Tonight's lecture, NASA's Next Big Thing, the Nancy Grace Roman Space Telescope, by Ori Fox of the Space Telescope Science Institute. I'm your host, Dr. Frank Summers of the Office of Public Outreach here at STSCI. And as always, I love to thank our wonderful tech team, Gary Gilbert and Grant Justice, for bringing you this web stream presentation. Our upcoming talks. Next month on October 1st is an empty slot that I will fill this month. And you know, if you're a regular viewer, that sometimes we get these holes in our schedule. And I got to tell you, over the summer is not the easiest time to recruit speakers. So now that everyone's back at September, I will recruit a speaker this month, and there will be a wonderful talk on October 1st. In November, we avoid Election Day here in the United States. So instead of on the first Tuesday, we'll be doing it on the second Tuesday, and that is November 12th. The talk will be There is Light in the Darkness by Elena Vardulaki of the National Observatory of Athens. So we're going to have an international speaker in November, as well as an international speaker in December, on December 3rd. Hunting the Stellar Undead, Gregory Sivakov of the University of Alberta. And if you want to remind yourself of these speakers, you can go to our website, www.stsci.edu/public-lectures, where you will find this webpage. In the lower left are the links to our webcast, not only our YouTube playlist, but also the STSCI webcast page. In the lower right is the box where you can sign up for our email. Also on our website, of course, are the upcoming lectures. And if you click on one of the lectures, you will get the full information about it, the title and description, as well as, after it's been recorded, links to the STSCI webcast and the webcast link on YouTube. Our email, as I said, sign up at the website. But if you want to, you can also subscribe to our YouTube channel, youtube.com/Hubble Space Telescope, all one word. And if you sign up, you will get new video notices and reminders of live events. Also, if you have comments or questions about our public lecture series, you can send them to the email address publiclecture@stsci.edu. Finally, our social media. We handle social media for the Hubble Space Telescope, for the Webb Space Telescope, and for the Space Telescope Science Institute on Facebook, X, YouTube, and Instagram at the handles there. You can take a screen grab of that and follow us all over the place. And now, news from the universe for September 2024. Our story tonight, a red, white, and blue nebula, L1527 IRS in the mid-infrared. Okay, so over the summer, there was July 4th, and July 4th has fireworks and everything. And we are not above pandering to a local holiday with some of our press releases. Matter of fact, I was looking through our press release archive, and we have used the term celestial fireworks over and over, often in promoting a press release near the July 4th holiday. But this year, we didn't go with a supernova explosion or a nova explosion or one of those explosive things to recommend fireworks. Instead, we went for the USA and a red, white, and blue nebula. So this is our red, white, and blue nebula to celebrate. That was done with a bit of celebration towards July 4th. The nebula is around the protostar L1527 IRS, okay? And I'll explain all of this stuff here, okay? First of all, IRS stands for infrared source, and that'll be important when we take a look at it later. Now, this is in the mid-infrared, so we're looking at 7.7 micron emission in blue, 12.8 micron emission in green, and 18 micron in red. And actually, if you think about it, white is the combination of red, green, and blue. So it's things that emit at all of those wavelengths. And I'll explain to you what the colors mean in this image, but first I really need to explain what's going on here, okay? First of all, this is a protostar. This is a star that is in the process of formation. Matter of fact, this is a class 0/1 protostar, so it is still accreting mass. It's still getting bigger, okay? And so what's happening here, you've got this sort of hourglass shape, and the material is flowing in from the sides to accrete onto the star. Actually, it doesn't accrete onto the star. The material flows in and it joins an accretion disk that's a very thick accretion disk that's around this protostar. And then from the protostar, the material, from the accretion disk, the material accretes onto the protostar. And in doing so, some of it will create huge energetic outbursts, okay? Lots of radiation and particles and a little bit of mass flowing out. But that outflow is going to be collimated by this thick disk. So it can't flow out sideways. It can only flow out above and below. So you get these collimated outflows and it ends up looking like the neck of an hourglass, okay? All right, so that is what's going on here. You've got a protostar with a thick disk around it and material and energy flowing out at the poles, all right? And so the red in the center represents the dense blanket of dust around the protostar, right in the detail. The white is the dust and some ionized gas. This is the stuff streaming away. This is the stuff that's been energized, okay? And then the blue is just the cooler dust that's further away. And we have a very unfortunate term for this. These are polycyclic aromatic hydrocarbons, or basically it's soot, okay? And that is soot that's radiating at hundreds of degrees, okay? So it's just warm soot that is there. So that is what's going on in this image. And this is the mid-infrared view that we just released last month in July, or I guess that was 2 months ago in July. It also, we have had a previous view of it with the NIRCam, the near infrared camera. It looks like this. It's a little bit more fleshed out because the near infrared can see more stars and things, but it can also see different temperatures of gas. So here we got the mid IR and the near IR. All right, and you can see the near IR gets further out away, okay? But the mid-infrared also gets that white stuff in there in turn the center that doesn't show up very well in the near infrared. And so we see a little different of an image between the mid and the near infrared. And one of the things that I think is coolest about this object is what we see when we look with visible light. And we see absolutely nothing. Okay, it's just black. Let me back up on this, okay? So there's that little square where L1527 IRS is, and this is some dark clouds in Taurus. And you can see a few stars in this area here, but you really can't see much in the Digital Sky Survey image. All right, if you take a much longer exposure and use the appropriate filters, and you process it correctly, you can actually see in shadow the dark clouds in Taurus, right? This is a wonderful image from, I'm going to put amateur astrophotographer in quotes simply because these people don't get paid to do astronomy imagery. Yizu Zhang, I found it on AstroBin, and it's a fantastic image. And if I get rid of that square, you can see that central region in here, that is the dark cloud L1527. And so L1520 IRS is an infrared source within the dark cloud known as L1527. The other thing that you note in the center, just to the left of this over here, okay, this is a dark cloud called Barnard 22, and that bright patch in there is called the Little Flame Nebula. all right, also known as IC 2087. Okay, and so there are these wonderful dark clouds out there that are really difficult to see, but there are some great images if you look out on the internet to finding them. And what you really know is that invisible light, you don't see much in these dark clouds. But this is what the Webb Space Telescope gives us. It gives us the ability to see in detail in the infrared light, both the near infrared and the mid infrared, and see an object that we never would see with Hubble or any other visible light telescope, right? This is why we need visible light telescopes like Hubble, infrared telescopes like Webb. We need X-ray telescopes like Chandra. We need telescopes in all different wavelengths to study different objects that show up at different wavelengths, and to see different aspects of objects that show up at many wavelengths. But this is a really cool object because it shows you something that we really couldn't see with visible light telescopes. All right, our speaker tonight is Ori Fox, and he has been at the Space Telescope Science Institute for 9 years. Most of it working on that mid-infrared instrument, the MIRI, in the James Webb Space Telescope Mission Office. But now he has transitioned to the next telescope, which he'll tell you about, the Roman Space Telescope. And his title, let me make sure I get this right, is Deputy Project Scientist. So he is responsible for really knowing everything about this telescope. He got his master's and PhD at the University of Virginia. Went on to do postdocs at the Goddard Space Flight Center, where he worked on the James Webb Space Telescope, and at the University of California, Berkeley. I did my stuff at Virginia Tech and UC Berkeley, so it's amazing the number of cross paths that we have in astronomy, where the exact same experiences that the astronomers go. And let's see, I asked him for a fun fact about him. He said he is a big baseball fan. He's been a big fan of the Washington Nationals, although he might consider rooting for the Orioles. And something that he and I also have in common, he is coach of his daughter's soccer team, and I was a coach of my daughter's soccer team many years ago. So, ladies and gentlemen, Dr. Ori Fox.
Okay, thank you for that nice introduction, Frank, and good to see everyone virtually over the internet tonight. I'm here to tell you about what I consider to be NASA's next big telescope. I mean, the Webb just launched a couple years ago. Hopefully, a lot of you have already heard about that. We had a nice public lecture series on that about a month ago. But it's never too soon to start thinking about the next big thing. And Nancy Grace Roman Space Telescope is just about 2 years away from launch, and I'm going to tell you all about it tonight. So I just had a little bit of an introductory slide here. Frank gave me a great introduction. This is a recent picture of me down at NASA Goddard Flight Center's clean room, where the parts for the Roman Space Telescope are already beginning to arrive and construction is beginning. So it's a very exciting time over there. A lot of the planning is now becoming a reality. Like Frank said, I am currently serving as the Roman Deputy Project Scientist at Space Telescope Science Institute. What that means is I am a liaison between the Institute and the science community to make sure that the science community has everything that they need to be able to get the science done once we have our telescope launch. That is what we call our functional responsibilities. On the science side of things, I study infrared astronomy and I have a specific focus on supernova explosions. That is the death of a star when it reaches the end of its lifetime. And we're going to talk about that a little bit today. I like to start my public talks with a little bit of background about astronomy itself. If you're a regular at this lecture series, maybe you know a lot of these things, but we probably have a lot of new people tonight. So I never think it's too basic to begin with the question, what is astronomy? A lot of people ask me this on the street. What does an astronomer do? And I think it's important to sort of frame this conversation. There's many, many different things. It's one really big puzzle, but I can probably boil it down to about two big things, okay? On the left, we have a very standard illustration of what we call our cosmological picture. This is understanding the origin and evolution of our entire universe, starting with the Big Bang and expanding over 13.5 billion years to the current present day. Then, on a more maybe defined level, another aspect of astronomy is understanding the birth and life cycle of both stars and galaxies and their associated planets. And so there's a lot of work in understanding that whole evolutionary process. Okay. So throughout today's talk, you'll probably hear references to a lot of different aspects of astronomy. And I want you to really keep this slide in mind. This is not new, right? We did not create astronomy in the past, 50 years or 100 years. It is something that humans have really thought about for probably since the beginning of time, ever since you were able to look up at the sky and ask what is out there. We've learned a lot about this in our history textbooks. But astronomy is just one way to understand the surrounding universe, right? We understand the universe also through religion, right? Religion asks very similar questions. Where did we come from? Where are we going? Art and music, understanding our environment around us. So this is why, right? This is considered a PhD. It's a doctor of philosophy in a sense, right? And these are pictures from a recent trip to Italy where we saw some of the first telescopes ever created. So people say to me, why do you study astronomy? And the answer varies depending on who's asking me and whether I really want to have a long conversation with them on the plane or not, right? But there are many different answers to this. They can be very philosophical, they can be very concrete, they can be very technical. But in the end of the day, you don't really need a good justification for doing anything that you're doing. You can just do something because it's cool. And that's my favorite answer. As an astronomer, I get to do what I think is just really cool. And I am very fortunate. This is a bit of a humble brag. I guess it's not so humble, but I had a recent appearance on CNN and they asked me that question. And I said, we are all astronomers. Ever since we are kids, we look up and we ask what's out there. And so I'm just doing the same thing that I've always been doing. But I can't steal that line. It's very common. A lot of astronomers say this. In fact, it was made famous by a very famous astronomer, Neil deGrasse Tyson, who, like many of us out there, look up to. And I really appreciated when he said this, and I've really taken that on, and I reiterate that talking point every chance I get. Okay, so let's get into the science. We're going to jump right in, okay? Like I mentioned, NASA has had a series of wonderful, great telescopes. Some of the most famous, of course, I think it goes without saying, is the Hubble Space Telescope. Most recently, we have the James Webb Space Telescope. Some people call Webb the successor, the big brother, the big sister to Hubble. Really, they are complementary spacecraft, okay? The Hubble was optimized, even though it was just about 2 meters, it was optimized for visible light. That visible light could only, and the size of the telescope could only look out so far in the universe. And so we ultimately determined we needed a bigger telescope that was optimized for the infrared. And that's how we built the James Webb Space Telescope. But there are still a lot of unanswered questions and certain questions that even the Webb can't answer, nor the Hubble. And the biggest reason for that is these questions require very big data sets, very big sample sizes. So if you remember one thing from today's lecture, it's that Roman provides very big data sets and very big sample sizes. It's not about going very, very narrow and deep in the universe. It's about covering as much area as we can. And that is why I like to refer to Roman as the next big thing. It is covering an aspect of phase space that neither the Hubble nor the Webb are able to cover. Okay. Here are some very quick fun facts for the Roman Space Telescope. The Roman is Hubble sized, okay, in terms of the size of its mirror, and it has equivalent resolution. Except unlike Hubble, which only had one detector, and Webb, which has a few more than that, right? Um, Roman has 18 4K by 4K detectors. These are state-of-the-art, top-of-the-line infrared detectors. And you can see right here in the middle of the screen a comparison of what we call the field of view between Roman, the Webb, and Hubble. In fact, Roman is 200 times larger in terms of field of view than JWST, and it is able to scan the sky 1,000 times faster. So here on the right is just sort of an illustration of the Roman, we call this the Roman footprint, all 18 detectors stacked over and over again across a nearby galaxy. And it shows you how quickly we are able to observe that entire galaxy. Observing that galaxy with Webb or Hubble would just take too much time and it is implausible. So we are going to be able to do that and very similar things with Roman. So why did we build Roman? Well, I've already given you some hints about this answer, but there are a couple very specific science drivers. We call these science drivers. And these are what sort of drive the design of our specific telescope. And there are a few, but I think there's three sort of big ones. One is, what is the nature of dark energy? The second is, what is the nature of dark matter? And the third is there life elsewhere in the universe? Okay. Today we're going to talk about dark energy a bit and also exoplanets where life may exist. We're not going to really talk about life, but we're going to talk about the planets. But a theme that I really want to get across today is that despite these science drivers, Roman is going to be a telescope for the entire science and astrophysics community. Because of the technology that is required to answer these questions, we are going to have a telescope that really enables all sorts of exciting science, just like Hubble, just like Webb. And the entire astronomical and science community will be able to take advantage of this telescope and make their own discoveries. And so even though we have a few science drivers, we have four very big science themes. We try to sort of package these in a way that you'll remember them. And what we do is we sort of increase our enumeration one by one, right? So we're going to do planets by the thousands, galaxies by the millions, stars by the billions, and ultimately probe all of fundamental physics. In other words, we hope and expect that Roman is going to do everything. And that's sort of what's encapsulated in this graphic in the bottom right of the screen. So who was Nancy Grace Roman? Nancy Grace Roman was NASA's first astronomer, chief of astronomy. She often has a nickname, the mother of Hubble. She had a vision very early on that we were going to need space telescopes. And she was able to do the politicking to build that consensus to move that needle forwards, which ultimately led to the Hubble Space Telescope. She also had a great technical background. She was not just a good astronomer, but she knew how to build things. So she was very involved on the NASA side of things in really having that vision for what space telescopes would look like. I was very fortunate, if you look here on the left-hand side, to have met Nancy Grace Roman. She came to a conference at our institute in Baltimore, Maryland, about 2017, which very unfortunately was just about a year or two before she passed away. And I do love this story. I had the honor of driving her home. She lived in Bethesda, Maryland, and She gave me her address and I put it into Waze, and it was something like 6,000 Connecticut Avenue. And I mistyped anyway, I wrote 600. And so we're following Waze, and she says, I don't think you're going the right way. And I said, well, you can't, you have to trust Waze. It's always right. There's probably a traffic accident or something. You have to trust technology. And she said, okay, okay. Anyway, we ended up at the wrong address. And I said, here we are. And she said, no, we're not. So I had to drive down Connecticut Avenue, down to 6,000 Connecticut Avenue. And we made it home, but I do like to tell that story. Anyway, Roman is making a lot of buzz. It's very exciting. Regardless of your political affiliation, Kamala Harris just visited recently. She's very excited to see all the action. And speaking to her here is Julie McHenry, who is the project scientist for the entire mission out at NASA Goddard. Things are happening. The reason people are coming to NASA Goddard, I showed that picture of me in front of the clean room, is that the technology and the hardware is actually starting to come in. Construction is becoming a reality. You can see the spacecraft bus. That is what you actually put the telescope onto on the left-hand side here. And on the right are the actual instruments arriving. These are the instruments that go on the back of the telescope and ultimately collect and record all the light for the astronomers to use for their science purposes. The light itself is recorded on these infrared detectors in the top right. These are about the size of your palm, and they cost probably close to about $1 million each. They are state of the art. They work just like the sensors in your digital cameras or even in your iPhone, except they're a lot bigger, a lot more sensitive because you need to be able to see to the very edge of the universe. So these are really cool and incredible equipment. Okay, so that's a little bit of the background of Roman, but now I want to tell you what makes this telescope special. And I think you can boil it down to about four main things, okay? Um, the first is that it is an infrared telescope. The second is that it is in space. The third is that it has a very wide field of view. And the fourth, this may not seem like a technical feature, but it's a very unique way, a revolutionary way in the way that we are doing science as a community, is that this is being community driven. And so I'm going to go through all of these points right now. So number one is that Roman observes in infrared light. Okay. The reason that we want infrared light is that Frank sort of gave us a little introduction to this. Infrared light has many advantages over visible light. One is that depending on the wavelengths that you're looking at, you're less prone to the effects of gas and dust, which is really important for a lot of science topics, but specifically for cosmology, which we are going to talk about at the end of today's lecture. The second is that the infrared is very sensitive to the high redshift targets. High redshift means targets that are very far away towards the edge of the universe. Okay, we'll go into some details about these in the upcoming slides. And like I said, it's better for cosmology. The infrared really helps with calibrating supernovae, which are used for cosmology as well. Oh, and it's worth saying what wavelengths are infrared light. The way I think about it is when you turn your electric stove on, right before it turns red, it gets hot, right? You can't see it, but it is hot. That's the infrared. When it gets too hot, it actually starts to glow red. And so the infrared is just longward of the red wavelengths. We typically say about 1 to 2 microns. The reason I mentioned before is infrared is great for detecting very high redshift events. This is such a cool concept that I really want to include this in the talk. Is our universe is expanding. We're going to come back to this throughout the talk. Our universe is expanding, and as our universe expands, it actually stretches light. You can think of this as the Doppler effect. Well, it is the Doppler effect. And it works very similar to a siren coming down the street where, you hear that pitch. getting louder, not just louder, but higher in pitch as it comes towards you, and then lower as the ambulance passes by. It's the same thing here. As the universe stretches, it stretches the wavelengths of light. And the more of a universe that light has to travel through, the more it actually gets stretched. And so if you're looking at things very, very far away, that light has been stretched so much that it is now not visible to our eyes anymore. It has to go be detected by an infrared sensor. Okay. And the way we like to think about very high redshift, very distant galaxies is sort of like a flip book where you're looking at the evolution of galaxies as they grow up. You can think about this as a photo album of your child. As you look further and further away, you're looking at light that left at an earlier and earlier period of time. So it's very similar also to, being at a baseball stadium where you see the bat gets swung and the sound doesn't reach you for another couple seconds. But if you have those good seats right behind the catcher, you hear it right away. If you're all the way in the nosebleeds, you hear that delay. So the further you are away from this light, the longer it takes to reach you. So in a sense, you're looking back in time. Hubble was only able to see something like 10, maybe 11 billion years ago, but we know that the universe is older than that, about 13 and a half, 13.7 billion years old. And that's why we built the Webb, because we needed the infrared light to see all the way back to these very early galaxies at the beginning of time when they were just little babies. Okay, so why do we put a telescope into space? We could build a much bigger telescope here on the ground, right? And in fact, there are teams building really big telescopes, 30 meters in size. The reason is that even despite the size, our atmosphere is turbulent, and it also blocks light at many wavelengths, particularly in the infrared. So let's talk about turbulence. So if you're looking up at the sky through the atmosphere, there's going to be not just cloud cover, but all sorts of thermal cells where you get turbulence in the night sky. And you can see here Jupiter, when you have, with the exact same equipment, when you have good seeing and bad seeing, that's what we call the atmospheric conditions. And that's just from the ground, right? And so you don't want to be contesting with this every single night, nor do you ever achieve even the same quality, particularly in the infrared. Here's an example of what the sky looks like in the visible and the infrared if you look at during the day. That's not a big surprise. If you look up, you see a blue sky. The difference is at night, visible light is able to penetrate our night sky and you're able to see all your favorite constellations. But guess what? If our eyes were sensitive to the infrared light, we wouldn't be able to see anything. It would look just dull and blue and gray again. That's because our atmosphere is actually not transparent. It's opaque to infrared light. So that's a pretty good reason for why we should go to space. And then, of course, you can go to space and boom, your infrared sky is just glowing, okay? All right, so that's 2 points about Roman. Number three is that Roman has a wide field of view. This is really just absolutely stunning when you think about this. This is not to scale, right? This is saying that some of the biggest programs in Hubble and now JWST are trying to tile the sky to get really big samples. Now, JWST is bigger and it can go deeper, right? We talked about this already. But it takes a long time to build up that sample, to build up that survey. It can take weeks, even months, to get about 1.6 square degrees of the sky with Hubble and now the James Webb Space Telescope. But with Roman, we are going to survey areas that come out to about 2,000 square degrees. I mean, you can't even put these two on the same scale. So this is going to be revolutionary. We are going to look at huge swaths of the sky. We are going to get huge data sets that dwarf anything that Webb is able to produce. It might not go quite as deep, but the sample size, you're going to be able to do all sorts of population statistics. That means that Roman's going to create very large data sets. Here's a reference, a comparison of Hubble's entire data archive over its 30-year lifetime. It produced 172 terabytes. That may sound like a lot, except Roman in just 5 years is going to produce 20,000 terabytes or 20 petabytes. Okay. And we are going to have to be able to make sense of all these data, right? And so when you hear the words big data, this is really a good description of what the community is going to have to deal with when they have Roman. And it's not going to be as simple as just looking at one or two objects at a time. We're going to have to synthesize large data sets and probably use machine learning and AI to make sense of, these populations. And fact number 4, Roman is community driven. This is perhaps, to me, one of the most exciting parts about Roman, because this really is my primary job, is to liaison with the science community to make sure that we have a telescope that meets their needs. And the reason that this is different than the Webb and Hubble is that the surveys are multi-year surveys. They're not small observing projects for small parts of the sky, right? We're surveying, huge chunks of the sky. And that means that these surveys have to be planned prior to launch. It's not going to go through a traditional observing proposal cycle. Instead, we really know what the surveys are for these core surveys, at least. And they need to be planned in advance by the science community. And so right now, this is happening as we speak. In fact, just an hour ago, one of the definition committees gave a town hall to the entire astronomical community, outlaying some of their ideas for how they are designing the survey for the high latitude time domain survey. And this is actually happening all week. And after these designs are done, they have to do all sorts of trade studies and analyses. It's going to go to a super panel, which will sort of merge all of the different surveys together. Each survey has a different science theme, and we're going to talk about some of those science themes now. Okay, so I mentioned there are 4 science themes for Roman: planets by the thousands, stars by the billions, galaxies by the millions, and fundamental physics. We definitely don't have time to talk about all of them tonight, so we're going to pick 2. And we're going to talk about planets, and we're going to talk about dark energy. Planets. Well, you might not know this, but the ability to observe a planet directly was not possible until 2001. Okay, you need very specific types of hardware and technology to be able to resolve a small planet next to a very bright and large star. This first detection was made for one of the dimmest stars. It's called a brown dwarf. And the planet itself was really big. You can see the relationship here on the left-hand side between the planet and the star. Technology has been evolving for the past 25 years, and we now have the ability to detect very small planets next to the central source. And one of the best ways to do that is with a coronagraph. A coronagraph essentially blocks out the central light from a star, and it's able to see all of the planets that are orbiting that star. So Roman does have a coronagraph. It is a technology demonstration. It is hopefully going to evolve into a future NASA mission, which is currently called the Habitable Worlds Observatory, but that will be much larger than Roman, with the specific intent of blocking out light from stars that likely have habitable worlds around them. This telescope is not quite big enough to detect Earth-sized planets around a single star, but we are developing the technology to be able to do that in space. There are many other ways to detect planets. A very popular way is to watch a planet move in front of a star and block out the light from that star. And it creates sort of a dip in the light curve, is what we call it. And that dip will look different at different wavelengths, okay? Because the size of the planet's atmosphere is actually different at these varying wavelengths. And so what you can do is look at the various wavelengths, and you're able to see how much of a drop that star has, and you're able to compare it to a model. And the model itself will basically tell you characteristics about that planet. So, for example, if the dip is not that large, it means that you have a lot of clouds. And if the dip is very large, it means that you don't have that many clouds. Okay, so you're able to derive lots of characteristics about a planet. And it just so happens that the filters that we are putting on Roman are designed specifically to accommodate very specific features in the spectra of different types of exoplanets that we are already aware of. Okay, now the trick is you need to be able to do this for a lot of different stars. You can't just go to one star at a time. And the beauty of Roman is that we are going to be able to observe, remember, billions of stars, hundreds of millions of stars in these different surveys over and over again. And we're able to look for at their light curves, right? We talked about this. The light curve is how that star's light varies with time. And when you see this big dip, that means that the planet is in fact going in front of the star and it's blocking some of that light. And so when we do this with a very large sample, we are able to constrain a lot of different properties. I talked about the size of the planet. We are also able to constrain things like the eccentricity of the orbits, and the types of host stars, and even some of the materials that the planets are made of. There's a third way that we're going to be able to detect planets, and that is what we call a gravitational lens, a microlensing event. And what's happening here is that a foreground star actually acts like a lens, just like you wear when you have glasses, where you're bending light from a background star. And I'm going to play this a couple times. The light from the background star is always moving in a straight line towards the telescope, but it's also moving in every direction, right? If you stood on this side of the star, you would see it. And if you stood down here, you would see it. And if you stood up here, you would see it. But it just so happens that this star is bending any light because of this lensing effect. This is, relativity. And it's bending that light towards the telescope. So that as a foreground star passes in front of a background star, that background star will change in brightness. And here is what the observer actually sees. You can see this back here. It brightens and it creates sort of a double brightening effect. But there's a catch. If the foreground star has a planet next to it, that planet will also be able and capable of doing a little bit of lensing. So watch how these two stars differ in their brightness, these apparent stars, right? The actual star is always going to be right here, but the apparent brightness down here is triggered by a planet nearby this foreground star. Okay, so that seems pretty complex, but if you have a survey that is looking at hundreds of millions of stars at a time, you're really able to see these blips in our own Milky Way galaxy sort of turn on and turn off, turn on and turn off. And what's going to happen is we are going to increase our discovery of planets in our Milky Way galaxy. Wait until you see this number. This is the history of planet discovery during my lifetime, at least. Here's 1989. And you can see no exoplanets were discovered until about 2000, and the first direct imaging was in 2001. And since that time, we have all sorts of different scientific techniques to discover new planets. And by in the past couple of years, we are now hitting about 5,000 exoplanets that we actually know about. This is sort of one of the examples I like to tell people when I say we're living in the golden age of astronomy. You have to realize 20 years ago, 25 years ago, we barely even knew that exoplanets existed. We thought they did, but we had no proof. Now we know about 5,000. But when Roman is done, we are going to know about hundreds of thousands of exoplanets using the techniques that I just described. Hundreds of thousands. I mean, look at this. We are going to think about exoplanets in an entirely different light. And this is really going to start to allow us to start asking questions about how many planets are in habitable zones? How many planets are rocky? What are the chances that we are going to find life with the next big telescope? Okay, so this is really exciting. Okay, so that's what I have to say about exoplanets. Now we are going to move on. I'm not going to talk about stars by the billions. I'm not going to talk about galaxies by the millions. I'm going to move along now to fundamental physics. And one of the big questions that we are going to ask with Roman is, what is dark energy? It is really mind-boggling that our universe is made up of about 96% of things that we just don't know about. People say to me, what do you mean we don't know about it? Well, there are many things we look out into our universe that we are able to see. It's obvious when we see other galaxies and other stars that this material is out there. That is visible light, and that is made up of what we can consider to be atoms, okay? But we are able to see effects through all sorts of various experiments and observations from other material that is out there, including dark matter. We see the gravitational effects, and dark energy, which you can sort of describe as anti-gravity. I don't want to say that, but it works opposite to gravity, okay? And we're able to see these effects everywhere. And so we know, Einstein knew that E equals mc squared. Energy is the equivalent to mass. And we know that the things we can see only make up about 4% of all the physical mechanisms that we are able to observe out in the universe. So where does this other 96% of stuff come from? It's really crazy. A lot of times we think we know everything, right? But we don't know 96% of our universe. So that's something to think about. So there are three big questions as we move forward. And I'm going to try to answer these sequentially. The first is, how do we know that the universe is even expanding? And we can owe that credit to Edwin Hubble, who is the namesake for the Hubble Space Telescope. In 1924, he went out there and he had an idea to apply a new technique in astronomy where he was able to measure the speed at which galaxies were moving. You have to realize that before the 1900s, this is really important to think about, we were not even aware that there were galaxies outside of our own Milky Way galaxy. And so in the early 1920s, when we first discovered that there were external galaxies, we were able to start as a community to do experiments on what these galaxies were doing. And one of the experiments that Hubble came up with was to make a simple plot of the speed of those galaxies versus their distance. You might think that's a trivial plot, but it's not. Coming up with a science discovery means thinking of a creative plot, and that's really half the battle. He probably should have won a Nobel Prize for this. The Nobel Prize didn't recognize astronomy back then as one of its core prizes, or really even part of physics. But so he never won the Nobel Prize, but this discovery in itself was fascinating because it showed that, knowing that he knew the distance to these galaxies, and when he measured the velocity to them, he showed that the further away a galaxy was, the faster it was receding from our own Milky Way. Think about that for a second. Why would galaxies that are further away be receding? And the main reason is, and he was able to put these clues together, is that our universe is expanding. And that means that no matter where you call home, galaxies are always going to be moving away from you. And a good way to think about that, there's different analogies that they like to make in the classroom. Some are a chocolate chip cookie. I happen to have a slide here for a chessboard where you start with pieces that are all at a given position on the chessboard. One piece is two squares away, and the other piece is only one square away. As you stretch that chessboard, you can think about the chessboard as our universe. all of the squares increase in size at a similar rate. But the two pieces that were closest together are only, still only one square apart, whereas these two pieces are still two squares apart, but they've doubled in distance in uh, in terms of travel distance. Okay. And so that really illustrates that the further you are away from another piece to start, the faster you're going to be receding from that piece. Okay. And so when we discovered as a community that our universe was in fact expanding, everybody wanted to know what sort of universe we live in. At that point, there were only three different options. The first option was that our universe was expanding, but would ultimately collapse due to gravitational pull. And we considered that to be a closed, decelerating universe. We thought that something might happen like a big crunch. That was the name in the 80s, the big crunch. Another option was that the gravitational effects of all the different galaxies in our universe was not enough to actually pull the universe back into another Big Bang, but that it would continue to expand forever. And it might slowly decelerate, or it might be this open decelerating universe. And so astronomers wanted to go out and test these different possibilities. And so to figure out what kind of universe we are in, we needed to look back in time. Okay, so we needed to go further back in time or at a larger distance, right? Distance and time, right? We learned about that in the beginning, than Hubble was able to do. And so that became the next experiment. And that's how we as a community discovered that the universe is accelerating. So in the 1990s, the tool that was needed to go out to these higher redshifts was a type 1a supernova. Okay, a type 1a, here's a fun video. A type 1a supernova is a special type of star that reaches the end of its lifetime and explodes with a uniform brightness. In this case, it's a binary system where you have a star that's growing in size over time as it reaches the end of its life, and it's siphoning off material onto its nearby companion, which is already a dead star that we call a white dwarf. That white dwarf never exploded. It sort of just shriveled up. This is what's going to happen to our sun. But as it pulls material from its companion star onto it, it becomes too heavy to support its own weight. And after it surpasses its this critical threshold in mass, it explodes into what we call a type 1a supernova. Okay, so this is another illustration. You have a star that's slowly dying, it's getting larger and larger. And as it goes past a certain point, it starts siphoning its material onto its nearby companion, which is this white dwarf. And once that white dwarf reaches its critical threshold, it explodes as a type 1a supernova. The key thing here is that because that critical threshold is the same in every single white dwarf, we have what we call a standard candle. And that means that based on the brightness of the explosion, we are instantly able to know how far away that object is. It's similar to standing in the middle of the street at night and seeing a car coming. You're able to decipher based off of the brightness of the headlamps how far away that car is. That's because you have a lot of experience on Earth understanding cars' headlights. In the same way, astronomers have been looking at type 1a supernovae for a long time. And when we see how bright a type 1a supernova is, we're able to determine how far away it is. So then we have to find the type 1a supernovae. And as we want to push out to larger and larger distances, we need better and better telescopes. And this is a real science example of how we found type 1a supernovae with the Hubble Space Telescope. And you can see here a picture of a galaxy in the top three different galaxies before a supernova explosion and then after. And that's really what half of the game of what astronomers, especially supernova astronomers, do. We look at before images and we look at after images in a lot of detail. And we try to find these things that go boom in the middle of the night. And we are able to determine based off of the color, the brightness, the spectrum, what type of supernova it is. And then we can make the same diagram that Hubble made 100 years ago, but with supernovae. And this really illustrates why supernovae are so powerful. Hubble was only able to go out, you can see here, about 200,000 parsecs. And that was just this little piece of what we currently today call the Hubble diagram. Now with supernovae, we are able to push out much, much further, many hundreds and thousands of millions of light years. And we're able to get the velocity with the spectrum and the distance using that standard candle technique. And then we're able to compare our observations to a model. This is a model of an empty universe. This is a very similar plot that I just showed, except in this case, we're plotting the brightness versus the redshift. Brightness is sort of a way of measuring the distance, and redshift is a way of measuring the velocity. Okay, it's just a more technical way to do this. And we're able to overplot as a community, not me personally, all of the different supernovae that we have discovered, both with the ground-based telescopes and with space-based telescopes, including Hubble. And what we start to see is as we get to higher and higher redshifts, which are, more and more distant from our own universe, we're able to see a bit of a divergence in our sample from the model of an empty universe. And so we can go and we can actually plot what we call the residual. This just means in a perfect open universe, you would have the supernovae, the data minus the model come out to be 0. But in our case, we actually find that there is another component. This component requires that the universe not just be expanding, but that it actually be accelerating. Okay, because what this is saying is that the supernovae that we're detecting are fainter than we would have predicted by a non-accelerating universe. We also have our other models down here, but none of our data sets actually come close to indicating that these other models are correct. And so we know now that we have an accelerating universe. Okay, so remember we talked about the different possibilities before, but it turns out that the answer is actually a flat accelerating universe. This was such a radical discovery. This is actually one of the other examples that I use when I tell people we are living in a golden age of astronomy. Just 25 years ago, we confirmed that the universe is not just expanding, but accelerating due to a mysterious force that we call dark energy. And so in 2011, three older white men won the Nobel Prize for discovering the accelerating universe. Adam Rees is right here at Space Telescope Science Institute and a major contributor to the Roman mission. So then the question became, what is dark energy? And the answer is, well, we don't know. That's why it's called dark energy, right? We don't know what dark energy actually is. There are a lot of different possibilities. There are many theoretical papers out there and propositions. One is that it is this mysterious vacuum energy that is typically referred to as the cosmological constant. Um, if dark energy is actually evolving with time, which it very well might be, then it is dynamic, which would be a very different physical mechanism than any vacuum energy. And there's also the possibility that there's a modification on gravity, especially general relativity. And that's why we have a picture of Einstein down below. That would be pretty radical because, gravity and, general relativity work very well for the most part. So this would require a very intricate fix to our understanding of whatever gravity is. But nonetheless, there are ways that we can test this, and the implications are actually pretty important because they can tell us whether how our universe may or may not end. And so this is really one of the key experiments for Roman. We know that the universe is expanding. We know that the expansion is accelerating, and we know that dark energy is driving it. And so we go back to this cosmological picture, And we know we started at the Big Bang. We know our universe expanded, and here we are today. And this is what the future may or may not look like. So to do this test, we really need a bigger sample. We need more data. That's a very popular phrase amongst astronomers. We're able to get our funding when we say our sample size is too small. Well, it turns out that this is true. The discovery of dark energy was made with just a few dozen supernovae. But we want to be able to distinguish between all of these different theoretical models that I previously listed. And you can see the scatter in this particular sample is just way too high. And so in order to
Occurring only once every
in order
500 years.
to take the next step, we need a much larger sample. So I'm going to play you a quick video that highlights the type 1a discoveries that are expected by Roman.
Occurring only once every 500 years or so in the Milky Way. But because there are so many galaxies, astronomers using current telescopes observe type 1a supernovae about 100 times a year. By comparing the observed brightness with the intrinsic brightness, astronomers can determine their distances within 6%. The Nancy Grace Roman Space Telescope, set to launch in the mid-2020s, will observe large patches of sky repeatedly, increasing the opportunities to spot these supernovae. Scientists predict Roman will see as many supernovae in 1 month as they've found in the last 20 years. Finding more of them will help astronomers refine the accuracy of this method, contribute to an improved three-dimensional map of the universe, and better understand how the universe has expanded and evolved throughout cosmos.
Okay, so the key point here is that we need to increase our sample like this. And you can see Roman is just going to revolutionize the field of supernova astronomy. And so as we reach the end of the talk, I just want to sort of give you the expected timeline. Here we go. Webb was launched in 2021, and Roman's not far behind. We're expecting the launch to be no later than May 2027. So this should really be on everybody's radar. And I think to end today's lecture, I'd like to just take a second and show you a simulation of a Roman deep field. So this is Roman going really deep in all 18 detectors. And I want you to just ponder the discovery space that is left. And I'll leave you with this. I've been, over the past year, I've been speaking with a lot of high-profile scientists in both Webb and Roman, and I said, what is the discovery that you are most excited for with all of these great new telescopes? And I am not lying. Every single one of them said the greatest discovery is going to be the question is going to be the one to the question that we still haven't thought to ask. So there's a whole universe out there, and I hope you're ready. We're going to discover it together. So thank you for your time and attention, and I'm happy to answer any questions.
All right. Thank you, Ori. That was wonderful. Great presentation. The Roman Space Telescope, I think you characterized it correctly, is going to be a new type of space telescope in that that's a survey mode, right? I mean, it's what was it? This first was called W-FIRST Wide Field Infrared Space Telescope.
That's right.
Yeah. Um, one of the things that you didn't touch on, okay? You talked about 20,000 terabytes of data, but I think a key point that the audience might not recognize is that it's going to have similar resolution to Hubble. Okay, so I mean, you've got this 300 million pixels per image, and the resolution. Give an overview of that.
Yeah, I mean that's a great point. You know, a lot of times you would think that you have to sacrifice resolution for area on the sky, but because we have because of the telescope optical design, combined with the fact that we have 18 detectors, and combined with the fact that these detectors are state of the art with 4K by 4K pixel resolution, we are able to achieve the exact same resolution as Hubble. And so what that means, right, is that we're not just doing survey science on, you know, there have been all sky surveys in the past where you lose in terms of sensitivity and resolution. You have large areas of the sky, but you can't quite build up the same statistics because you don't have the resolution to resolve the objects or the sensitivity to go deep enough. And so Roman really combines the best of all worlds, right? You get the resolution, you get the sensitivity, you get the infrared, you get all this, and you're able to build data sets where with similar quality to Hubble, but hundreds, thousands of times larger.
Right, and this is going to, as you said, 20 petabytes of data. Where are we going to store all this? We
Yeah.
astronomers aren't quite used to working with that much data. I mean, I know we can learn from like the particle physics community on that.
Well, you know, everyone should invest in Amazon. It's going up into the cloud. And I mean, there will be ground backups, but everything is going up into the cloud. And in fact, this is a very new thing for astronomers. Astronomers like to download data. They like to work on their own machines. They like to write their own software. But this is going to, in many cases, be prohibitively expensive in terms of time, in terms of money. Most laptops or even desktop machines won't be able to handle these entire data sets. You might be able to look at small fractions. Um, but to really analyze the data, the astronomers are going to have to get used to working in the cloud. And that is going to be seamless in some respects, but it's also in terms of you're able to move a lot of your code up into the cloud. But our techniques are going to have to change, right? Because again, instead of looking at one or two objects in a lot of detail, we're going to have to look at a lot of objects in a little detail. And so really creating tools to look at 20 petabytes of data and make sense of it is going to be a real challenge to the next generation of astronomers. And right now we are building out that community every single day, trying to do training, trying to brainstorm, trying to develop new tools and software to be able to support all of that effort.
Right. I mean, it's a cultural change in astronomy that's going to have to happen. And this is actually one place where the younger researchers will have an advantage because they will be growing up with this idea in mind. Whereas those of us who've been around for a couple decades, it's harder for us to make those changes in what we're doing. So I think that this is, in terms of not just NASA's next big thing, it's astronomy's next big thing with both, Roman and Rubin, and we're just going to have tons of data
Yep.
to process. All
Yep.
right, so we've had a ton of comments on the YouTube chat.
Okay.
Grant's been following it closer than I have. So, Grant, would you come on and let us know your favorite questions from the YouTube chat?
Yeah, absolutely. Yeah. Just first off, great chat today. Thank you to all of you who are positing questions and joining in. I'm going to start off with one that I like, being a non-astronomer. Um, how many diffraction spikes are we going to have on Roman?
That is a good question. I am going to guess uh, 4, but I'm going to take a rain check on that. I'll admit I don't know that answer, but I'm pretty sure it's going to be 4.
Okay, so
If any, yeah,
the optical path similar to with the struts, as similar to Hubble?
exactly. That's my thinking, but I actually have
Just
not
like
explored that in
stretched
detail.
out.
What's that? Oh yeah, well, no, there's just
Stretched.
going to be a lot more of them.
All right. Okay.
And related
Go
to
ahead.
that, some people might be a little confused with the 18 detectors, and it's a sort of a weird pattern. I'm assuming that's just allowing for room to get all the electronics in for those 18 different detectors.
Yes, that's exactly right. It's a pure technical driver there. That's
Right.
right. But it's funny about the diffraction spikes. For people in the know, the that is one of a lot of times people ask, well, how can you tell a Hubble image from a Webb image? And that is one of the tricks. So
Yep.
now we are going to have to think about what the trick is for distinguishing a Roman image from Hubble or Webb. But I think the short answer to that, it's just going to be a lot bigger.
And you answered this during your talk, but it's something that I want to reiterate both for the audience and myself, because Hubble is always the first observatory that I think of. It's the one that's been around since I've been around, and it's like the bar that I have. But it's also, Hubble came out before we had like Razor flip phones. Like everything involved has come a very long way. And the first thing I saw when I saw Roman's field of regard was something more like what's the exoplanet finder? TESS? I think it's
Test.
TESS, right?
Yeah.
Yeah. Yeah, the first thing I thought was TESS. Oh, it's a big wide field. It's just like a viewfinder. Like it's gonna find things to point another telescope at. No, it's gonna do all of it. And that didn't really click with me until hearing you talk about it, because yeah, everything's
Yeah.
come a long way in 33 years.
Well, it's a great point. I didn't speak about TESS at all, but for people who don't know are not aware, TESS is NASA's Planet Finder mission, and they use a very similar technique that Roman uses in the sense that they look at a very specific part of the sky, and they're able to look for these transits in terms of the stars dimming and brightening. But they also don't have quite the same resolution as Roman. And they don't go into the infrared. So Roman has, like I said, the best of all worlds. It combines Hubble Webb, but it also, yes, it combines TESS, and it is going to knock TESS, out of the water. But that's and people that work on TESS are very excited because they are going to be able to you bring a lot of the skills that they've been building for TESS. In fact, a lot of the TESS work is done in the cloud already, and they're expecting that they're going to be able to bring a lot of these techniques to the Roman mission.
And, I mean, these were the ideas. The Kepler mission, the TESS mission were to develop the statistics and the understanding of the exoplanet population that Roman has been able to use to adjust their filters and everything and say, oh, these are the most effective ways of finding these 100,000 exoplanets that you plan to find.
That's right.
It's almost like we do science to do more science better or something. It's almost like we learn. All right, let me get on to the next one here. Boop, 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 boop. What special capability does Roman have to search for extrasolar planets using gravitational microlensing that differs from how, like JWST would do it, or for example?
Well, again, the answer to almost every question, almost, is sheer size and field of view, right? It is using very similar techniques as Webb. The difference is that with that field of view and the survey design, right? So we didn't talk a lot about the survey designs tonight, but maybe this is a good opportunity.
Please.
I tried to keep to touch on them and then get into the science because I think it's a lot of fun to think about, what's out there. But you have to lay the groundwork to answer these questions. And like you said, you have to think about how to optimize your surveys so that you maximize discovery space. And so when you're thinking about these microlensing events, you're trying to think about filters, you're trying to think about cadence, you're trying to think about parts of the sky, how many times you hit a field, which fields you actually want to hit, to maximize the amount that you're going to be able to find different microlensing events, because every microlensing event is different because it's based off of the size of the planet. It's different based on the size of the host star. So you want to be able to capture as much variety, as big of a sample of these microlensing events as you can. So going back to the question, right? JWST is phenomenal for capturing one microlensing event at a time. But if you want to capture thousands or
Oh.
hundreds of thousands, you need Roman. And when you do that, you're able to make plots where you have sort of I don't have a plot in this particular talk. I was just looking at one this morning though, where you're able to basically plot the different parameters of your planet in what we call phase space. So it means like something like planet size versus, orbital period. Those are two very big topics, right? And you can see all the ones that we already know about based off of other telescopes where we've done things one at a time, where we've been looking, even in a certain type of phase space because we have a visible telescope, or the TESS, or maybe it's not that big of a telescope, for example. Roman opens up an entirely new aspect of this phase space. It's going to discover types of planets that we were not previously able to discover. And so when we start to explore those, then what's really cool is you can say, whoa, look at this segment of the population over here. What's going on? Why are these big planets at this orbital period? Maybe we need to do follow-up, right? Maybe we need to ask more questions. Maybe we need better theoretical models. So it really pushes science and transforms science in that way.
I love that. I hadn't considered that. I'd always thought, again, coming from Hubble being the first thing in my brain, I'd always thought gravitational lensing being like a singular type of event. Like,
Yeah.
the fact that we'll be able to do multiple is already blowing my mind.
And the statistics of, if you need rare objects, you need a lot of data to find those rare objects. Okay. And if you've got 100,000 planets instead of 5,000 planets, you're going to find those ones that are, much rarer.
That's right.
So this is, to me, one of the greatest things in terms of the golden age of astronomy, is that we're getting to do what we could only do with Star Trek in our imagination. We're actually exploring other planets. Now, we're not flying there, but we're actually getting all the data. And to me, what's really exciting is the understanding of the atmospheres of planets, because not just characterizing the sizes of planets and how many there are and everything, but really starting to characterize the atmosphere requires a ton of different data, because a lot of them, a lot of the planets that we observe, we can't get much information about the atmosphere. So
Yeah,
big data is really important for that.
I think we're just now starting to be able to resolve some of that with JWST, right?
Well,
Like
JST can do it, but it can do it one at a time, et cetera.
Yep.
We're going to get a lot more data. Big data really gives you, your view into the depths.
Where will the telescope be orbited? What have we learned from previous deployments like JWST to protect it from things like micrometeorites? And is it going to be like a stationary Lagrange point? Is it going to be like a low Earth orbit?
Yeah, this is going to be out in L2, just like JWST.
Okay.
One of the big drivers for that is, again, the infrared. The Earth is one big glowing heat ball, and we want to stay away from that, especially in the infrared. The L2 also offers important in observing opportunities in terms of continuous viewing zones, which are critical for time variability, where you're observing over and over again. You don't want that sun to come in between you and that field. And so that's important. In terms of what we learned, well, I'm not going to jinx anything, but I mean, I'm not going to say it, but I need to address the fact that this is certainly not as complicated of a deployment as Webb, right? It's a single mirror telescope,
It's not a transformer.
It's not a transformer. That's exactly right. But as we like to say in our industry, space is hard. There's nothing that's ever easy. So I am not going to say that this is going to be easier than Webb. It's going to come with its fair share of challenges. Commissioning a wide field telescope in space is going to be something new. That's going to be fun. Um, and in terms of the micrometeor zone, for those of you who are not aware, there are micrometeors size of pebbles that are always going through space. We know about these. They are a calculated risk. There was one that hit Webb early on in the mission, something like 2 months in, which was described as a once in a lifetime event, and it hit 2 months in. It was on the distribution, and it made people wonder whether we actually had our distribution of events incorrect or something like that. I think what we're finding is that it really was a once in a lifetime event that happened right away. But nonetheless, we are able to point the telescope in a very safe fashion to avoid ever going directly into any micrometeorite field. So we're always pointing away. And we've been doing pretty well since. I don't know exactly how that's going to apply to the various observing schemes for Roman, but now it is definitely part of our planning system.
Wonderful. So in your talk, you talked about the community surveys and how they will take a large percentage of the time. What percentage will be done in survey mode, and what percentage will be done for targeted mode with the Roman?
Yeah, so the numbers are still being finalized, so nobody should quote me on these final numbers, but the core surveys are going to take up roughly about 75% of the mission lifetime for the first 5 years. Of course, Roman may last longer than 5 years, but the nominal mission is 5 years.
We have a good track record with that.
We have a good track record, of course. And then 25% will go towards what we call general astrophysics programs. And these may be the traditional pointing programs that you're thinking about, but we also hope that they are going to be more surveys that are defined by the community, but potentially for complementary science or additional, science that might add on to the existing surveys, or and might not be as specific as somebody saying, I just want a single image of this particular field. Of course, that will be possible, but it will go through a competitive proposal process. But the truth of the matter is that what we're really hoping is that with our surveys, we are going to have so much data that when people apply to work on Roman, they are going to be applying to work on the cloud, not with getting new data on the telescope. And we're hoping that they are going to be able to make use of these 20 petabytes in ways that go beyond just these initial science drivers, because it would be a shame if we get all these data and we're still only doing 1 or 2 science projects, right? So we're really hoping the community is able to think outside the box, think differently than they have in the past. And we hope that the majority of proposals that come in will actually be archival and not observational.
Or I just recognize that you haven't stopped your screen share.
Oh yeah, well that's
oops.
okay.
No, it's all right. It's just something that normally
we forgot to.
We forgot about it.
I wanted everyone to know my conclusions, So
Okay.
I'll stop.
I've been looking at them for quite a while. Now you can see all 3 of us together.
There we go. Okay.
Oops.
It's all right. It's all right.
So,
but yeah, that underscores your final point, which is the question's still unasked, right? That people will be, when we come up with new questions, they'll design surveys to answer those questions. All right, Grant, what else we got?
a couple if we've got time for it.
Oh yeah, we got another 5 minutes.
Cool. How will Roman interact with ground survey telescopes like Rubin LSST?
Oh, that's a really good question. So for those of you who don't know, Rubin is a very large ground-based telescope. that will be also surveying the entire sky. Surveys are a big thing because the field realizes the power in these big data sets. Okay, so that's not unique to just Roman. People are catching on. And Rubin is from the ground. I told you that there were limitations from the ground, and Rubin definitely has some of those limitations, but it's great because these are two very complementary telescopes. Because Rubin, even though it faces some of those limitations, especially in the infrared, it's a really big telescope in the optical, and it's designed to be able to do the large sky, and will be able to cover a larger area of the sky than even Roman can, because it's such a big telescope and it will be on the ground. Which gives it a little bit more flexibility. So what you're able to do is combine the different wavelengths and the different resolutions, and not just spatial resolutions, but time resolutions, right? You can imagine that Roman won't be able to be everywhere at once, but Rubin won't either. But if you are able to combine their two data sets, you're maybe able to put together very unique light curves. You saw light curves were a critical part of the exoplanet science. I didn't really say this, but it's also a critical part of the DNA science. Okay, so there's a lot of combinations there as well. But what we're really excited about is this idea of what we call joint pixel analysis. And what that means is that from the ground, Rubin will not have quite as good of resolution as Roman, but it will have some critical wavelengths that will be useful for a lot of the different science experiments. Roman, on the other hand, will have the resolution, and you're able to sort of convolve the better resolution with Rubin's resolution and extract all that additional information out of the Rubin data sets and combine sort of one, you know, master data set, which will be really incredible. Now, the trick to all of this, and this is a technical challenge that we haven't quite solved yet, is being able to have both data sets on one cloud infrastructure. We're two very different teams. One's NSF, one's NASA, right? So this is where the right hand has to talk to the left hand, and we'll see if we can get it done. People are trying really hard, but to be able to house all those data simultaneously on one cloud infrastructure would be just really incredible.
That's something
Yeah.
that comes up in our chat often is, oh, well, what does like Roman do? What does JWST do? Like, what are their individual, like they're intended, all of these, even the ground-based, all work together. They all have different individual things that they do better, or they have specific fields of view, or they have specific like spectrographic fingerprints essentially that they work within. They're intended to work together, not as separate, but like equal wholes. Like it is a system of systems.
Yeah, this is the kind of the vision that the National Virtual Observatory was sort of ahead of its time in trying to. This is the application for which NVO was looking towards creating the virtual observatory projects of, I don't know, they're 15 years ago. Yeah, so this is now going to be a requirement moving forward. All right, do we have time for one more question? Actually, I had an interesting thing. You showed Hubble's initial redshift diagram, right? And then you showed the one with lots more data and extending further out. And it occurred to me that, all right, well, the supernova type 1a plot you showed that only had a little bit of data is sort of like the Hubble diagram in its early stages. And after this, you're going to be able to extend that much richer and stuff. So we're sort of like in that same spot on this different question.
Yeah, I mean, one day they'll look back and they'll laugh at us, right? And then they'll say, look what they could do in 2024. That was nothing, So.
That's the goal, though. That's the whole point from the beginning.
Right.
One last question.
One last question. Go ahead, Grant.
Will Roman be able to make concurrent spectroscopic measurements of many objects within its wide field of view?
Yes, so that's a very good question. I didn't even talk about the spectroscopy capabilities of Roman. Roman will have what we call a prism spectrograph, where it's called a wide field slitless spectrograph, basically, which traditionally, when you take a spectrum, you want to lay a slit because that allows you to block out all the light from other nearby objects, which if it gets dispersed would overlap onto your particular object and ruin your spectrum. And you want a very nice slit and a very clean spectrum. But here we don't have that time or even capability because we have this huge wide field. We don't want to be using it one slit at a time, right? So we're just putting in this prism and we're going to look at everything in the field and we're going to be able to disperse it. And we have incredible scientists and astronomers that are building software to be able to extract spectra from all these really complicated fields where all the spectra overlap each other. But we now have techniques. If you take the data in the exact right way, you're able to deconvolve all of those different spectra. And these will be all very low resolution, low signal to noise, but they will be another critical piece of the puzzle in terms of understanding all of the individual objects that we're looking at.
Right. And we'll have a database of spectra of
That's right.
so many objects. I mean, JWST is doing some of that already with the Ulysses program and on Hubble as well, that you're building this database. This is just going to, again, expanded yet another factor of 10. All right, we are getting to 9:30. That is our traditional cutoff time, an hour and a half for it. Thank you very much. This was great. Next month, October 1st, we have an unknown talk by an unknown speaker, but it will be there. Please join us. I guarantee you it will be wonderful. Thank you all for attending tonight, and have a great day.